Okay, is the font size all right? So what I want to do today, last class, right, is give you an example of a full API of something, right? And I chose that to be linked lists, essentially. We're going to discuss the fact whether we want to know whether they're linked or not. When do we want to know that, and so on. Before we go into that, the makeup lecture for Thursday, there's a recording available which introduces trees. In the form of evaluation trees for expressions, right? Though trees are not limited to that application, but it is one way to experience this data structure, and it is the subject of one of the homeworks. So yeah, hopefully you won't have too much trouble going through the lecture, understanding the examples there. There's some code that you can play with in order to practice, and then go ahead and do the homework. I think I told you last time as well, the problem sets are not specifically related to expressions, right? We just want a convenient way of generating trees, right? And looking at typical operations on trees, like, for instance, finding the number of nodes, finding the depth, and so on and so forth. We're going to move along in the same direction, right? And talk about a different data structure, that of linked lists. And what do we want to illustrate today? Most of you have had the experience of a language like Python or R, right? Where you do have high-level data structures available, such as lists. At that point, you don't quite think how the lists are laid out in memory, right? You're thinking that a list is a sequence of elements, and there's a bunch of operations that you can do on them, right? So you can append them, you can put one element at the end, you can prepend one element in front, you maybe can delete one element from the middle, you can find out whether an element is inside or not. You can select the element with a specific rank, and so on and so forth, right? So for you, the object list, right? In your head, it's an abstraction that is capable of handling those operations, right? It doesn't really matter how the list is laid out in memory. It could be as an array, really an array, but then when you think of an array, it's not so easy to extend it or reduce the size, right? Or it could be in any other kind of memory organization, as long as the operations are supported, right? So we want to accomplish two things here. One is we want to isolate the implementation from the use. Whoever needs to use it doesn't need to know how it is implemented, all right? So that's a very important design principle. And then we want to pick one implementation and implement that data structure, and realize in the process that if later we change our mind and want to change the implementation, right, we could change that implementation and still have the client code work. Whoever is only using it is writing code to use it, right? That code won't break. I can change completely the implementation and that code won't break. So these are very important software design principles, okay? Now, we talked a little bit about that before, right? When we talked about strings and we were thinking of, what would be strings in Python and how come in Python, we immediately have the length available for the string, whereas in C, we have to iterate through the string and find the \0, right? So that's because in higher level languages, in higher level languages, we don't use primary data structures as we use in C. We use combinations of data structures to accomplish that, right? So how would you implement, and let's discuss the Python case, because that's probably more interesting and will provide a better intuition, right? So in C, what we have is an array, which is a contiguous part of memory. This is somewhere in memory, right? And it ends with a \0 here, right? \0. Well, supposedly it's a \0, right? And what we use in C is the pointer that points straight to the top of them. What we would do in Python is we add a little bit of extra wrapper, or wrapper, right? We add a structure, right? In C, you would implement it as a structure, which will have a pointer to the beginning, will have a pointer to the end, and we'll probably have the length here. Maybe the length is not necessary, because you can subtract the end from the beginning from the end, right, and find the length. But actually, the secret is that you do need the length. Why? Because we're using we're not using ASCII characters as we used so far in C. We're using Unicode, and Unicode characters don't necessarily have constant length. So the number of bytes in the string isn't necessarily the length of the string, right? So you want to have the length, and then what you get from Python as a string is this guy, right? So you're getting this little structure, and this little structure has extra pointers, right? And these pointers help with a lot of stuff, right? They cache a lot of stuff, so then whenever you need to find the length, you just pick it up from here, right? You have to be careful that whenever you expand the string, you also have to append the length correspondingly, right? If you shrink it, you have to update the length correspondingly, but then the length is always available to you as an immediate operation, right? You don't have to go and scan the entire string to find out, right? And having these wrappers around the entire infrastructure, data infrastructure for our collection of stuff, right? So a string is a sequence of characters, which is essentially a collection, right? That helps a lot. But what you see as a very simple object has actually a very complicated memory layout, right? And we're going to try to do the same. Today we're going to try to add a little bit of a wrapper and make it a little bit more complicated and gain some advantages. The important advantages that we're going to gain are the fact that we can completely separate the implementation from the use. So what is a linked list? Well, it is a structure that looks like this. We allocate a little structure with two fields, right? One is the piece of data, which could be an integer or a character, but necessarily something of constant size. If we can't have something of constant size, then how can we make it of constant size? Louder. So if you have something that is not of constant size, like a string, right? String can have variable lengths, or an array. How can you make it constant size? You haven't internalized C yet. Put a pointer to that thing, right? So that's always right? I have something that says I don't know. Oh, I know the size of the pointer to that thing necessarily, right? It's only 64 bits. So either this is something like a integer or a character, right? Something whose size I know for sure, or if not, it can be something else. But typically, what I have here doesn't matter, right? This is a pointer to the next element, which has exactly the same format, right? Pointer to the next element. Right, and we reach the last element, and this is null. The last element has this pointer called next equal to null, right? So typically we will have two fields, data and next, right? And we have this chain. And if we were in C, if you would learn data structure in C, they would tell you, oh, I have a pointer here, and this is a list. But guess what? This is not good enough for a list. Right, and if you would do this in any other language, you wouldn't do this in any other language. So you want to put a wrapper. The wrapper will give you a pointer to the first element, a pointer to the last element, and maybe a length. Right, so this goes here, this goes here, and this is what you call the list.
This is what doubly linked list.
This is a simply linked list. Right, the singly linked list will, the doubly linked list, each element will have another field, and you would also go in the opposite direction.
So why do you need to store the last element? Because usually single linked list.
What if you want to add one element?
Oh, okay.
Right, I mean you still can,
Yeah,
but you have to iterate, right? Whereas if you have the helper of the last element, it takes constant time,
okay.
Right? So and obviously if you use a doubly linked list, which nobody would stop you from, right? You're going to get more advantages. You're going to get more help with a variety of things, but you have to keep it consistent, right? So every operation, there's more stuff to keep consistent. All right. So for instance, let's say you want to advance very fast through the list. So you can put an array here of pointers. So this guy goes to the half. This guy goes to the quarter. This guy goes to the eighth, right? And then if you want to go to a certain rank, right, you can do it very fast, right? You can jump and you can do it logarithmically, right? So you can invent all sorts of little additions to, help with your efficiency, right? But there's more stuff to keep consistent at that point, right? So we're going to keep things simple because we only have 1 hour, 1 hour and a half, right? So single linked list with a little wrapper, that's our what we call the list object, right? And we're going to define an API, what we call an application interface, right, with a bunch of functions that we consider to be essential. And we're going to implement those and show that the abstraction doesn't leak, that whenever we use that API, we don't need to understand what's underneath. Cool. Yeah. All right, so I'm going to include stdio h as usual. We're going to have a main, and I am going to write tests this time. So we're gonna write some tests that are going to help us with checking whether the code is correct. Right, but we don't accept input from the beginning. It's going to look pretty much like the layout that we have for homework. Okay, so let's define the data structure. So we're going to say struct list, and let's make this a type def. Fortunately, the keyboard is not as good. All right, so not sure if you've seen this before. I'm going to explain shortly what it is. So we're going to have a piece of data, and for this exercise, data can be just an int. All right, and then we're going to have struct list star next. All right. Oh, sorry. Not list. Let's call this a node. So this is the element in the chain. Let me explain everything that is going on here. So this name is generally optional, right? We don't. Whenever we define a structure, we don't have to use a name there, right? If we do, then we don't actually need a type def here. Automatically from that point on, this is a standalone type, struct node. I can reuse it at any subsequent point as a type, whenever a type is required, I can write struct node, and that's syntactically correct. All right. Now, but most of the time we don't need that, right? Because we just write a structure and we define a number of variables, and we don't use type def. We just define the variables here where the node is, and that's it. Except for the case when we have recursive definitions, right? This is a recursive definition. So this name is referred to here as well, right? And I can't have a recursive definition without a pointer. All right, why is that? Well, as the compiler compiles and parses this, when it reaches this point, it doesn't know yet how large struct node is going to be, right? But it knows how large a pointer to struct node is going to be, because it's going to be as large as any other pointer, right? So that's the real trick. So pointers are fine. They're going to all have the same size. So when it reaches here, right, it can use, it has seen this before. Struct node, it has seen before. This node that you see here, it hasn't seen it before. And C is a bit stupid in that sense. You cannot have forward references. Everything has to be backward. Everything has to be previously defined or prototyped, right? So we need to give a name here, because otherwise we wouldn't be able to have a recursive reference here. Now we want this type name to be, we want to have a convenient type name. I don't want to write struct something all the time, because that's too long, and it's sort of not at the same level, not uniform when compared to, for instance, int, right? I would like just a type name that can be used as any other type name. So this is the element of our chain. And now we want the wrapper. So we're going to have type def struct. And now, because I'm not going to have a recursive reference, I don't need to give it a name. So node first and last, and int length. All right, and we're going to call this a list. Right? So we have defined the types of our data structure. So the user only needs to know that this type exists and the operations for types, right? The user should not need to know the definition inside here and the definition of a node. All right? So whatever we write inside main, we will never refer to those, right? Unless we want to really, verify something. All right, so let's start with building one list. So we're gonna make an empty list. Right, so we're gonna say list star and we have to allocate a list element. So we're going to say list star result equals list star malloc of size of list. All right, then list first equals is assigned list last is assigned. Man, the keyboard is atrocious. Null, and then list length is 0. All right, and we return, sorry, why did I say list? This is result. and we return result. All right, so this creates an empty list. We need to include stdlib.h for malloc. All right, and unfortunately, this is not enough to perform any tests. We're not doing anything interesting yet. All right, so let's add elements. So we're going to have a function that we call append element, right? List star append element, and we're going to have a list star L and a int element. Now we have two options here, right? The first option is to return a completely new list that doesn't share any elements with the previous list. The second option is to actually clobber the previous list by extending it with one element. All right, and Python, for instance, offers both options. Right, you can extend. I can't remember which of them. Extend. But we can find out. Right, so if I say L is 1, 2, 3, and then I say L.append 4, is this correct? All right, so append performs the operation destructively, right? So the previous list doesn't exist anymore. Whereas we can also do L plus 5, right? So we get a new list, which is which has a new value, but the old list has the same old value, right? So we have both options. We're not going to have time to do both, but remember always that both options are available, right? It's possible to do it in two ways. And always doing it non-destructively. Non-destructive operations are a lot cleaner, but always are also a lot more difficult to implement. It's easier to mutate in place, at least from the point of view of C, as compared to copying the original value into a new object and modifying that one. Okay, so in general, we're going to be destructive, right? Because that's the easier choice. But remember that in general, this is not the cleanest way to do things. All right, so we're going to append elements. We're going to essentially implement the operation that we have seen here in Python. All right, so let's see, what do we do here? We have a list L, and we have two cases, right? What are the cases? Yeah, the list is empty. How do we know if the list is empty? The last is null, first is null as well, right? So it doesn't make sense to have the first null and the last non-null, or vice versa, right? So both have to be always null. Perhaps it's better to write a function that tells us whether a list is null or not, right? This will make things a lot more readable. So int is empty. F list star L, and we're going to say return L first equals null. All right, and then here we can check if is empty L. All right, so what do we do then? We create a new node with the element, right? So we're going to have node star n. Man, it's gonna drive me crazy, this keyboard. Node star malloc size of all right. Now what's going to happen is that we're going to need this a lot. All right, so we better actually make it into a separate function. So we're going to have a node star new node of int data, and we're going to say node, let's just pick it from here. So we allocate, and we say that n next should be equal to null. You see, at this point we don't know what's going to be the next element, and we don't want to leave it unassigned. Always, never leave it unassigned. And n data equals data. Return n. Right, so now this makes things a little bit simpler, because we can say that node star n equals new node of lm, right? And then since it's empty, we can very easily say that L first is assigned L last, which is assigned n, and then L length equals 1. Okay, so we handle the case where the list is empty. Now, everybody's comfortable with this? Have you seen this before?
Is it like the dot in Java?
The dot in what sense? So this is like the dot in Java.
The method within the class.
But you have, so you have like it looks like a ternary operator, right? We have an equal, we have a chained assignment, right? So the way this is evaluated in C is like this. Actually, if I put the brackets in, it's not wrong. It's syntactically correct, right? So it is right associative. The assignment is actually an operator which has a side effect. All right, so when I perform this operation, this is an expression. It's not a statement. This is an expression. The value of the expression is the right-hand side. So in this case, it's going to be n. And the side effect of this operator is taking n and copying n into the memory location of this guy. Right? Do you see how it goes? So it has a value and a side effect, right? So because this thing has a value now, which is n, I can go and say L arrow first is assigned that value, right? And I can chain as many assignment operators as I like, because they're right associated. Okay, so this is one of the shortcuts of C. There were people who were criticizing it as well, but in general I find it pretty clear and not very harmful. So I still use it. Else. So we're appending to the end of the array of the list, right? So we're going to have to assign to create a node as well, right? So if I have to create another node here, since I have to create a node at the beginning of each of the branches, I might as well factorize this piece of code outside, right? I could just copy it from here to here, and we only create the node once. right? So then, now the list is not empty. We're assuming that L arrow first and L arrow last, both of them are non-null, right? And I can say that L arrow last, arrow next is assigned node, right? Then L arrow last is assigned what? So right, so this guy points up to here. Previously, this was null, right? Now I'm coming with a new node with my new value here, right? This is the data. So I want this to be part of the list. One thing that we're doing, what we're doing here is, instead of having the blue grounding, we have a new arrow, right? So points from this guy to the new node, right? So this is last, right? So last arrow next is equal to, this is node, right? All right, so we put the data, the new data, as part of the chain. What else do we need to do?
But if you already have L last, you put N in it, right? In L last.
Am I not overwriting whatever was there? I need to append, right?
Oh yes.
All right.
So L last next becomes the new N, right?
N last dot next becomes
Node, which is N, right?
this node, right?
Yeah.
But then I also have, for consistency, I also have to move this arrow here, right? I have to remove this arrow and move this arrow here, right? Yes? All right. So then I'm going to say L dot last equals node, right? Equals node, which is N. The linter is correct. Okay. And what else do we need to do?
Sorry, the L dot last dot next.
Uh-huh.
Oh, because you don't want to overwrite it, right? So you. Because L dot last.
Because the element needs to know what's the next one, and I need to change the last one to point to the last one, the new last one as well. This is a linked list.
Oh, okay. Yeah.
Okay, it's clear now? Everybody is following? All right, so we have just added an element. Okay? So it's easy to add an element to the end. Is it easy to prepend an element? Yes, it's not too difficult either. Right? So, but I mean, of course, we like to add first and remove after that. But we want to write a test. We want to get the point of writing a test, right? So let's remove an element from the beginning, right? We're gonna discover that it's not so easy to remove from the end because we have to scan the entire thing, right? But it is easy to remove from the beginning, right? And then we can write a little program, right, that tests our correctness. We can take a number of you can take some numbers, put them one by one, append them to the list, then remove them from the front one by one, and check that they are the same numbers, right? And that will sort of give us the feeling of correctness. So let's remove from the front. So list star remove from front, which would be sort of a DQ operation, but let's not jump the gun. And actually, this can be void, right? But let's get into the habit of returning, because here we're saying append element. All right, so we're appending element, but the list is there already, so this can be void. Let's just have some consistency. And then we're removing from front from the list, but we're not returning. We might want to return the list or not necessarily, so let's make this void, right? The list is there, it has changed its value. So in removing from the front, again, we have two cases, right? So list star L. Again, we have two cases. If is empty, L, what do we do then? We have a bunch of choices, right? One thing would be to do nothing, right? Silent. That's very bad, right? But you know, sometimes can be useful in very niche situations, right? Typically, you don't want to do that, right? Trying to remove from the empty list should be signaled as an error. And whenever you try to remove something from the list, as a client of the code, you should, or any collection, you should make sure that the collection is not empty. Right? So one thing we could do, we don't know how to throw exceptions. C doesn't have exceptions at the language level. There's a way to simulate them, but we're not gonna go there. It's an advanced topic. So we're going to simply print an error message. And the very convenient exit function will help us there. I don't need to put an else here, right?
Is it convention to avoid this kind of functions, or to return like int like 1, 0, 2?
You see, you're inside a function here, right? Yeah. So you're exiting from potentially a very deeply nested call. Right, so exit essentially bypasses all the returns. You could, obviously you could, right? We're too early in the game to complicate the code that much. All right, so we could return an error code that tells us whether the operation was successful or not. Right, but this is still not wrong, because if you check whether the list is empty or not, right? If it is non-empty at the point of calling it, you're guaranteed to be successful, right? So, but in general, for in complex programs, it's good to have as much diagnostic as possible, right? So it's probably a good idea to do it. All right, so now we have a non-empty list. Right, so we definitely have a first element. All right, so our result equals L first. Right? A very important thing that people tend to overlook at this point, and I'm going to put it above because that's where it should be. Well, actually, I can't put it above, right? it might be cleaner to say here n. All right, and then n next is assigned null. Extremely important. Source of a lot of errors. Now, actually, it would be good, nevertheless, to return the node that we're removing, right? And actually, we don't want the node, because we're exposing, if we're returning the node, we're exposing the internal implementation. We want an int here, right? So what we want is the element. Okay? So n next equals null, in which case, actually, we don't need to do this. So normally, if we were returning the node, we do not forget to null the object. But int result equals and data. And the graceful thing to do would be to free n. So we have mallocked the node at some point before, right? Somewhere here, we created the list by appending elements one after another, right? And then each time, right, we created the node with a new node. So we used malloc to allocate. We should return that memory back to the system. We're saying that we don't need this node anymore. So we say free n here, right? That is the opposite of malloc. In malloc, we're asking the system for memory. In free, we're giving the memory back. And we're returning the result. All right? So now we can write, pardon?
The length is changes.
And the length changes. Very, very good. Yes, absolutely. L length minus minus. All right. We have written a function that checks whether a list is empty. Let's also write a function that returns the length. Man, it's incredible how this cursor jumps around. All right, and now let's write a small test. So we're going to say test one. Append remove elements. So for int I equals 0, say I less than 10, I plus plus. All right, we're going to start with a list that equals new make empty list, right? We will do append element of L and I. All right, then for int j equals 0, j less than 10, j plus plus. All right, if all right, let's get an element. So int lm is remove from front. L if lm not equal j, printf test failed and exit -1, let's say. All right, if the test failed, it didn't fail, what we want at the end is to have an empty list, right? So if not is empty L, right? Again, so I tell you what, I'm going to take these two and put them in a function. So int test, actually void test failed, and I'm gonna put a number here, which is the test number, and I'm gonna say test %d failed \n, the variable n. Let's align properly. And closed bracket, done. All right, and here we're going to say test failed 1. This is test 1. All right, and if not is empty, again, we're going to have test failed 1. Printf, and then let's have yet another function called test passed. Void test All right, so now we have a test. I think this bracket is not needed. So let's see how this works for us. GCC -o lists. Let's see. Lists. All right. Test 1 passed. Yay. Seems very, unceremonious, right? So if you want, you can add a little bit more output, saying, right, as you remove, we can come here and say printf extracted %d from list, and we can say the value lm. Right, so that will give you maybe a bit more confidence, right? So we have inserted the values from 0 to 9 into the list, we remove them, right? We know at this point that our program is correct. Okay. Personally, I don't like that much output, so I am going to delete this. But when you're doing your own testing and development, it's up to you. All right. So let's try to prepend values, right? And then what can we do, right? We can prepend the values, then we can remove them and see that they are coming in reverse order, right? So we can have another test. So we're going to say void element int lm, and so before we go there, notice that inside the test, right? So the test is about this much, right? So we never need to know that there exists an arrow length, there exists an arrow first, there is an arrow last, there is an arrow next inside any of the list, right? We're operating with, this is the only thing we know, list, and the functions that we have defined, also those are the ones that we need to know. And this needs to always be the case. If in this test at any point you're saying arrow first, or arrow last, or arrow next, you failed to provide a clean API. Okay? It means that the abstraction has leaked, right? By providing this barrier, we're saying we're providing an abstraction barrier, right? That's a very common thing. I think we talked about this before. You don't need to know how a car is built and how the engine works in order to drive a car, right? So you don't need to know how the list is built and what are the internals of the list in order to use the list. What are the handles of the list, right? Like the car has the pedals and the gear shift and the steering wheel, right? The handles to the list are these procedures. What's inside them is not the user's concern, not the client's concern, right? So you need to know what are the functions. You don't need to know, and in principle have an abstraction of what they perform at the abstract level, but not know how they are really implemented. Let's expand this a little bit. All right, so a prepend element. All right. So what should we do now? So again, we're going to have two cases, right? Can be empty or not. I need the list. That's very true. All right. So if is empty, L. All right. What's a very quick shortcut? How can the case for empty, how can I solve it very quickly? Louder. Very good. So if the list is empty, it doesn't matter whether I prepend or append. Right? Very good. So and always try to discover opportunities for reusing code. Return append element L. Right? So I don't need to put an else, because if we go there, we return, we would never reach the next statement. So now we're going to, it's going to be very similar to append, right? Just that it's going to, instead of using the last, we're going to use the first. So L first. The important thing that I wanted to steal was the creation of the new node. And I apologize for trying to copy and paste so much, but it's really not the best keyboard. So we create a node. All right, so the node dot next would be equal to L first, right? Since this node is going to become the first node, its next element has to become the old first, right? Once we have done that, L first can become n, right? And that's it. Yes? Clear for everybody? All right, so let's go and write test 2. Prepend and move from front. So what do we do now? We're going to I'm gonna play a trick, right? So I don't want to be bothered with variable names from the previous test, and I'm just going to add 2 brackets here, and then I have just created a separate scope. And I can do that, and that works in a lot of languages. Would work in Java, would work in JavaScript. You can do the same, right? So the interesting thing now is that the scope of L is only up to the closing brace. Will end here, and I don't have a danger of a name clash with the next test. I don't have to remember that, oh, L is already used as a name and I have to avoid it, right? So I'm going to say again, list star L, and well, again, let's copy as much as we can. All right, so now instead of appending, we're going to prepend element. And we're expecting the elements in reverse order. So we're going to start from 9, and we're going to keep going as long as j is greater than or equal to 0, j minus minus, right? And we remove front, and if element is not equal to j, we say test failed, and this is the second test. Else if is empty, and at the end, if not is empty, again the test has failed, and otherwise the test has passed. Okay, so we can check that the test is passed and the second test has passed. Okay. All right, we don't have a lot of time, so let's do one that is a bit more involved. We should do many of them, right? So thinking of Python, we should have a function that extracts a range, right, from this index to that index. We should have a reverse. We should have a sort, right, and so on, right? So everything that is available at the top level for a list in Python, we should also implement. So let's try to do to retrieve the element at a given rank. All right. So we're going to say, call it get element at. So we're going to have that will return an int, and we're going to have a list star L and an int index, right? So first of all, the index has to be positive, and we should check that. Less than 0. What am I doing? I'm in the middle of main, yes. We should be here above the. All right, so how do we when we get upset and want to exit? Okay, here. So unable well, maybe negative indices, illegal index. All right, we can say exits 2 here. Right, so now there's another error case, which is if the index is greater than the length, right? And actually we should add that here. So, or IDX is greater or equal than length of L, right? Then the index is illegal, right? We're going to consider that the index is going from 0 to length minus 1. So very simple for no initialization, or do we need initialization? I think we need initialization. Node star n equals L first. IDX greater equals 0, I think. And then we have IDX minus minus, and node, n equal is assigned n next. And this is incorrect. I should have greater strictly than 0. So if initially IDX is 0, we're getting the first element. Yeah, this is it. And there's nothing inside. So I iterated through the chain until we reach the element that we need. And we can return and data. All right. So test number 3. So what kind of test we do right now? To check that this is working correctly.
Just add stuff to the list.
Yes.
Then if you get index of n, then you should get the same number back. If you
Right.
do that loop, right?
So we create a list with, let's say, numbers from 1 to 10. Yeah, let's try a little variation on that, and then we try to get all the indices one by one, and we want to find the corresponding number. Right, and maybe we want to go with the indices not necessarily in increasing order. Maybe we want to go in increasing and decreasing order or something like that. Right, so test 3, check at given indices. All right, so again, I'm going to create a scope, right? And I'm going to have a list star L equals make empty list, I equals 0, I less than 10, I plus plus. So let's append element L, and I'm going to say I times 10, just make it more interesting. Then for int j equals 9, j greater equals 0, j minus equals 2. All right, so we're going to go to index j, right? But we don't, I mean, we're going with the indices in downward direction, and we were looking only at the odd indices, right? So now if what was it? Element at. Get element at. Element at L and J not equal J times 10. Right, in this case, we're going to have test failed. This is test 3. All right. And actually, we don't need the curly braces here. And let's go through the other, the even numbers in increasing order. So for int j equals 0, j less than 10, j plus equals 2. And again, if get lm at lj not equals j times 10, test failed. All right, so we're missing a semicolon here. N is undeclared in at line 76. Of course. So we're going to have to take this one outside. And test number 3 passed. Another thing we can do now is, let's say we remove a value from the front, right? And then everything shifts by 1 position. right? So this would also be interesting to check. So we could say that remove from front L. We don't care what we removed, so I don't care what the first element is. And now for int j equals 0, j less than 9, j plus if get lm at L and J not equal to J plus 1 times 10, test failed. Okay. So it continues to pass. All right. To make things nicer, one thing you should always have and easier to debug, we should have started with a function that prints the list, right? So let's add that as well. Print list star L, and we're going to just print all the elements on one line. So for node star n equals L first, and not equal null, n equals n next. On the printf %d space and n data. So this will print everything on one line. Let's put at the beginning of the list square bracket, and at the end of the line, we're going to put a closed bracket and a \n. All right. So let's make our test a little bit more friendly. So we can say printf test1, and then here we can say printf constructed list, and then print list of L. And right now we have test1, right, and we have the list, right, and we say that test1 passed, and we can be nice for all the tests. Now, as we are removing from front, right, we can say here printf list after removing %d colon, we have lm here, and then again we say print list of L. All right, so you can see how the list evolves. Right? Once the test passes, let's add a bit more space so that it's nicely formatted. And we can do this for each of the tests, right? We can try to find more reporting so that you get the feeling that things are actually happening, not just having a very a silent Boolean test that doesn't tell you as much, right? So let's try to do this for, this is test 2. And this is test 3. All right, and each time let's report on the constructed list. All right, so this is test 2. We can do the same here. And then for test 3, constructed list, we check the indices. Then we remove something, we print the list again. And well, something like that. You can definitely do better than what we've done so far, but at least this is a start. After removing the first element, right, so now the tests look a little bit more verbose. Right, so you can see that in the first test we're constructing a list, right? Then we remove elements one by one. We can see how the list is shrinking, right? And we end up with the empty list at the end. You notice here that the list is empty, right? And for the second test, you notice that the elements are in reverse order, right? Again, the list is shrinking, and we end up with the empty list. Yeah, similar here. All right, so we have some means of reporting. So this is about it, right? Normally we would want to expand this. You will have some opportunity to expand it in the final homework, right? The code that you have there differs a little bit, right? Not conceptually, but it was written at a different time, and I don't think I have I have done it in exactly the same way, right? So you might find small differences. So it would be good for you to look a little bit at the support that is already provided, and you're going to have to enhance the API for the lists, add new operations. Any questions? Cool. All right. So I extended the deadlines for the first two. The first two homeworks, right? Again, it's flexible, but not overly flexible. Remember that. I mean, don't just gamble it, right? Don't come in the next moment and say, "Oh, I would like an extension," because I'm not sure. I'm going to find throughout the next week when exactly I have to submit the marks, and I have to do the marking, and I'm going to try to let you know that beyond this date, it's actually not possible to extend in any way. And then as the deadlines, as the submission closes, I'm going to release the solutions, right? So you have a sample. Questions are not really difficult, and then if you look online, you're going to find solutions. All right, I don't think my solutions are in any particular way better than what's available, because they're very easy ways of, they're very simple questions, right? But yeah, hopefully this was useful to you. A little bit, eye-opening and appetite whetting, right? You feel ready to tackle this on a larger scale next time when you approach it. Cool. Thanks. So it was nice working with you. I really enjoy doing this kind of stuff. So it was really nice to have this opportunity.